I'll talk about what are the limitations of transmission electron microscope. So as I was just mentioning to you, here is a quote I've taken from a famous textbook. All of us who are studying microscopy, we usually start by reading this book from Williams and Carter on transmission electron microscopy. I kind of like this, so I put it here. It is better to know the forest before you start looking at the veins in the leaves on trees. So the sample size, for example, if I want to have transmission in an electron microscope, so that is the electron beam, if it has to pass through my sample, if I have an electron beam like this, the thickness of the sample cannot be beyond a certain number. I'll draw an analogy here. For example, if I have an X-ray, most of us must have got an X-ray radiograph done at some point. So people who are, let us say, half a feet to 1 feet in width, or people who are slightly more bulkier, are tested with X-rays, and then you can see how your distribution of your bone, or if you have a fracture, how the crack is, and so on. If I look at an inorganic material, if I take a block of aluminum, for example, X-rays can penetrate through a 1 meter cube thick aluminum block when I image such kind of a material. If I go to an electron microscope, beyond a certain thickness and beyond a certain atomic number, electrons cannot penetrate through a sample. So what you require is typically the thickness of a specimen should be less than a few unit cells. If I assume that the average thickness of a specimen is around, of a unit cell of a specimen is around 10 angstrom, the ideal specimen thickness should be somewhat around 1000 angstrom or 100 nanometer. Even in some cases, when I want to do some extremely high resolution studies or get some meaningful spectroscopic data, I would want to have the specimen as thin as possible. So the thinner the better if I want to have a specimen in transmission electron microscope. So as a ballpark figure, the thickness of the specimen should be less than or equal to 100 nanometer to get some basic imaging and diffraction information. But for high resolution, it can even be as low as 20 nanometers, or with the recent trend, you can also have single layers such as graphene or MOS2, which are just one freestanding layer of atoms as well. So on these kind of systems, if you control the dose very well, you can get some beautiful information. But most of the cases, when I want to get high resolution and spectroscopic information, I would like to have specimen as thin as possible. And in addition, when I look at the construction of the microscope, I'll just draw a brief schematic here. If I call this as my condenser lens, and if this is my objective lens and I place a specimen somewhere within my objective lens, if I have a source here, an electron beam going through my sample, it has to penetrate through my specimen and then go, and I get information which is recorded below the specimen on a screen. So what is happening here is, if I have a three-dimensional object which looks like a cube here, so let us say I place A at these corners, and if I have B at these corners, if I just zoom into my object, and if I give you an example of how an object might look like, the image I record from this would have something of this sort: A superimposed over B, so be careful. In a transmission electron microscope, always the information I record is projected information. So I do not know how my objects are placed in the third dimension. So in order to get this information, there are techniques called as tomography, with which you can get where the positions of the object of your interest are. That is a slight deviation away from this particular point. But always remember, in a transmission electron microscope, the information you record is always a projection of a three-dimensional object onto two dimensions. The images we record always have superimposition of the three-dimensional information on a two-dimensional plane. So this is actually called as projection limitation in a transmission electron microscope. So when I have information averaged through the thickness, it is always advisable to take images at several tilts. So if you draw a parallel to how you see a movie in 3D, you're recording information of an object from two different cameras at a different angle, and you use either stereoscopic imaging, or depending on what kind of spectacles you use, you can have polarized spectacles now, where you can form a three-dimensional image of an object. Likewise, if I have a feature like this, if I want to see that this is a three-dimensional object in a transmission electron microscope, I have to take multiple projections. I have to take a projection like this, another projection like this, and a projection like this. So in reality, with the limitations in the construction of a microscope, I cannot turn an object completely 360 degrees. There is something which I have as a limitation. So when I get a three-dimensional information from a sample in a microscope, in a TEM in particular, I should get series of projected images, and I have to do a mathematical reconstruction to get three-dimensional information. And moving on, you also have electron beam damage. I was talking about the positives of electron beam damage just a short while ago, where you can structure a sample, a two-dimensional material, section small parts. But in reality, if I use some kind of materials, a few minerals or polymers or organic materials, when I use the modern microscopes which are operating at 200 or 300 kV, more often than not, I cause a damage to the sample. There are different kinds of damages which you have. You have something called as ionization damage, you have knock-on damage, you have different kinds. But this affects in particular polymers, organic samples, specific minerals, even metals. I would say aluminum as well, if it is not very thick and your beam currents are high, while you are getting some kind of information of recording some EDS spectra or mapping, you might actually make hole through an aluminum sample in a transmission electron microscope, even at 200 kV. I can show you the examples a little later. So this is what you have in electron beam damage. How do we contain it? So as I increase the accelerating voltage, the electron beam damage increases. So what I can do is, I lower the voltage. So I was telling you a few minerals, for example, quartz can show damage even at 125 kilovolt. And carbonaceous materials typically have a threshold of 86 kiloelectron volt. So you lower the accelerating voltage of your microscope, and you also lower the electron beam dose. You can use a combination of sensitive detectors, and you can use electron beam which is not having a very high dose, and you can still image. So essentially, when I am looking at sensitive materials which can undergo damage under an electron microscope, I have to actually define a suitable experimental window, and then I start imaging. So this is what you have in cryomicroscopy. You often have minimum dose microscopy with cooling of a specimen, cryo-electron microscopy. I'll not go into this particular topic in this course right now, but there are ways in which you reduce the electron beam effects and to limit the electron beam damage. So there are newer instruments with faster cameras and faster detection systems. So if I can record an image before the damage happens, I still get some meaningful information. So there are a combination of various techniques that you can do to minimize electron beam damage and get meaningful information. Moving on, the biggest limitation. So when I talk about an electron microscope, the simplest thing that comes to your mind is a scanning electron microscope, and then a slightly more complicated one is a transmission electron microscope. And in a transmission electron microscope, like I was mentioning, your specimen thickness should always be less than a few hundreds of unit cells or a few hundreds of angstroms, ideally less than 100 nanometers. So when I say thin, it is a relatively thin specimen. If I have a material which has a very high atomic number, for example, if I have gold, tungsten, platinum, perhaps even a 40 or a 50 nanometer thick specimen might not give me atomic resolution information. Likewise, if I have silicon, carbon or aluminum, I might even get some high resolution information from even 100 to 120 nanometer thick specimens. So how thin specimens are needed? So like I just mentioned, so in aluminum alloys, even 1 micron is thin enough for 100 kV electrons. So you can still see something, some kind of a contrast from a 1 micron thick aluminum sample as well. Initially, when people were using 1 million electron volt microscopes, you were preferring to have thicker specimens because the beam damage is significantly higher. But like I was mentioning, 100 nanometers or 50 or even 10 nanometer thick specimens are good enough to get meaningful information. Now, what is the limitation here? When I have such thin specimens, we often come across questions on what is the effect of the large surface and how realistic are the changes that I do to a specimen, how do they correlate with a bulk sample, are the questions that you'll always come across. I'm just telling you one important difference that you should remember throughout the course. I've said something called the sample and a specimen. So when I'm doing some analysis on a sample of, let us say, aluminum, I have to prepare it, I have to section it, cut it, thin it down such that it is electron transparent. And commonly, this material, after thinning down and preparing it to be ready for TEM analysis, you call this as a specimen. So if I talk about the present trends in electron microscopy, where is this particular field heading to? Like I was telling you, from 1940s to 1960s or 80s, people were more looking at building robust, reproducible data that can be obtained from microscopes. And the idea was, how do I improve the resolution? So there were about 400 to 1 million electron volt microscopes, a host of them. Even today, there are a few instruments in Japan which are still operational, which are running at beyond 1 million electron microscope. So the idea was, I have to improve the resolution and achieve better and better and better resolution in the microscope. So till about 1980s to 1995 or 2000s, I think in around 1998 is when the first trials on the aberration correctors were successful by Harald Rose, Maximilian Heider and Knut Urban. This was done at the Forschungszentrum Jülich on breaking that 1 angstrom resolution barrier and getting the aberration corrected microscopes into the market. The trend of improving on resolution kind of saturated. So by about 2005 to 2010, there were commercial electron microscopes with aberration correctors. So people understood that you always need not go to a 1 million electron volt microscope, but if I have a suitable combination of aberration corrector and intermediate accelerating voltages, you can get sub-angstrom resolution even at 300, 200, 80, 60 or even 30 kV. So you have most commonly intermediate voltage electron microscopes. So the breakthroughs in spherical and chromatic aberration have revolutionized this. So you get energy filtered TEM imaging, you can get images or resolution of features less than 1 angstrom quite regularly these days. And it is now possible to image under live conditions as well. So what exactly are you doing here is you're applying an external stimulus to a specimen and you can investigate atomic level changes in situ. And there's another new trend which is coming up where people are modifying the microscopes a lot. For example, there is a large drive to look at ultra fast electron beams in the microscope, where you're reaching the femtosecond level electron pulse to get information from samples at extremely controlled doses. There is some kind of effort being done to integrate multiple tools together. That is, along with an electron column, people are trying to get in an atom probe column into the microscope as well. This is being done again at Forschungszentrum Jülich and at Rouen. So there is effort going in a direction where you are bringing in two different techniques together. There is something called as ultra fast spectroscopy system, ultra high vacuum systems where you can do deposition along with the microscope column. So there are a lot of advancements going on, and perhaps in the next 3 to 4 years we'll see more of these kind of microscopes. So from a stage where you've been looking at improving the resolution and breaking the 1 angstrom resolution barrier, we are now trying to use microscopes as tools where you can manipulate matter, change sample, get complementary information from various techniques, doing in situ imaging, doing correlative microscopy, and also bridging two different techniques together. So there is effort to bring in two different techniques together, or sometimes even more complementary techniques together in a single instrument column. So talking about the example of advancement using aberration corrected microscopes, let me just show you a quick example from one of the systems that we studied very recently. So here is an aberration corrected microscope, and from this particular kind of an instrument, it is quite common these days to get atomic resolution information. Here is an example of strontium titanate that you have, and you see the atomic columns of strontium here and titanium here, and if I do a compositional mapping, I can distinctly see the strontium atoms and titanium atoms, and here is a composite image. So this has become more or less a standard practice over the last 20 years or so, where you're having aberration corrected microscopes and you're getting atomic resolution information very consistently. And like I was mentioning, with these microscopes, with the presence of a corrector, what you have also achieved these days is improving the gap between the pole pieces in the objective lens. And what does this do? You can bring in different kinds of holders where you can introduce various kind of stimuli. And here is an example where we've tried to grow some gold nanoparticles inside a liquid inside the transmission electron microscope. The image is drifting a bit, but this is just to show you that within a microscope now you can also synthesize materials, and while this is going on, you can simultaneously get the structural and compositional information as well. So to summarize, transmission electron microscopy has started as a technique where you can start getting information from materials down to a few angstrom level, and we've broken the angstrom barrier, and now microscopes have evolved into tools where you can do manipulation of matter, real-time changes to the material, and get complementary information, which makes it an extremely powerful technique. So we've seen the trends in microscopy, in transmission electron microscopy, the improvement in resolution, the advances in development, what kind of developments are going on, where you're trying to bring in more experimental facilities into the microscope. Now, to start with and to understand how the microscope functions, let me recall this image which I showed you earlier. In this particular slide, you can see a stereo microscope, a compound microscope, and a transmission electron microscope. And if we flip the image in the middle, this is how the layout and the components of the transmission electron microscope were introduced. Now, let me show this in a little more detail and give you a ray diagram of how the construction of a transmission electron microscope looks like. So here you see that in the top you have an electron gun, and then you have the condenser lenses followed by the condenser aperture. In modern day electron microscopes, where you are trying to achieve more and more higher resolution with a field emission gun, and also when you are using probe corrector or an image corrector, you typically have something called as the condenser objective lens system. And here is where you have the third condenser, or some of the manufacturers call it the condenser mini, and so on. And then you have the objective lens which is at the center of the microscope. Now, the objective lens is the heart of the microscope. This is typically a copper coil which is similar to a solenoid, and what you have is an electromagnetic field that acts as a lens. Remember, the construction of a lens, which we will see in some time, is made out of some kind of a very good conductor, typically copper, which is wound like a coil, and this behaves like a solenoid, like I was just mentioning, and you apply fields as high as 2 Tesla. Now, because you have fast moving electrons here, to confine them into a path along the optic axis of the microscope, and for various functionalities, we use largely electromagnetic lenses. All of the above lenses that I mentioned also are actually electromagnetic lenses, and this particular construction here shows you some sort of a side entry lens or a split pole piece lens, where a TEM specimen is introduced from the side of the electron microscope column. You also have the intermediate lenses, the projection lenses, or some manufacturers call them the illumination lenses or the diffraction lenses. All of these together form an image, and then you have the detector which is below along the axis of the microscope. Now, when I compare it with the image here, and if I look at the breakdown of each of the components in a little more detail, you see on to the right, this is from the manual of this particular microscope only. You have a filament here which is a thermionic source. You have 2 beam deflectors. You have the first, second and third condenser lenses. You have the stigmation coils. You have the spot alignment system, and then you have the deflection coils for the condenser and the condenser mini lens. All of these together are actually in this particular location in the microscope. Now, if I go further down, I have the objective lens system. In fact, it will be a split pole piece kind of a lens. I will show an image a little later, and here is where your specimen is introduced into the microscope column. So, with a side entry holder, the specimen goes in here, and I have the deflection lenses or the projection lenses, and you have the fluorescent screen to record the image here, which is shown here. This is a schematic and a sort of a diagram which gives you a broad overview of the arrangement of the components of the microscope. Now, to get a little more information and a little more detail, let's do a walkthrough on this particular microscope here and see how the components are arranged, because there are quite a few components which are not shown in this image, but they are essential to run the microscope. For example, you have the high tension tank, you have the electronic console, you have the chillers and so on. We'll see how commonly these kind of systems are arranged together to let your electron microscope function. And it is important to know, no matter which system you are looking at, how this particular layout is and where these control systems are, because in case you run into any kind of a trouble, at least to understand the first level of troubleshooting, it is always good to know which component is where and how it is functioning. We've seen the ray diagram of a transmission electron microscope, and we've drawn comparisons with an optical microscope. Right now, we are next to the JEM 2100, which is a lanthanum hexaboride filament operated TEM. This microscope runs at 200 kilo electron volts, and here are the various components of the microscope. As it was discussed or informed a little earlier, this portion is where you have the electron gun. In this case, in this instrument, we have actually a thermal emitter. It's called as a thermionic emitter. And then in this portion, you have the condenser lens, and over here you have the objective lens. So in this microscope, you have a side entry holder, and over here you have a split pole piece type objective lens. What you see here is the condenser aperture. Here is a hard X-ray or a shielding aperture, and this is your objective aperture. If you go a little down, all over here is where you have your projection lenses. When you start imaging, you start by aligning the microscope by starting with each of these individual components in this particular sequence. It is not a hard and a fast rule that you always stick to the sequence, but it is a healthy practice and it is easy to remember if you start by aligning your emission system, condenser aperture, and then you load a specimen over here, you adjust the specimen height, and then you start imaging. Once you start imaging, you record the data over here. You see the data on the fluorescent screen as you see here. And if you go further down, there's a camera below. And on this microscope, we have a CCD camera on which you record the digital images. In the old school microscopes, you actually had photographic plates and you were exposing the electron beam and opening a shutter and recording the images on a photographic plate. So this is general layout of a transmission electron microscope. Now if I move behind the instrument, so we'll look at general layout of how a transmission electron microscope is laid over in laboratories in general. What you have is the main instrument column here. You have the high tension tank behind the microscope here. So the high tension tank is essentially acting like a step-up transformer where you're withdrawing power from the main line either at 100 or 230 volts, and then it runs through a loop over there, and you have the high tension tank acting as a step-up transformer. So here is the cable which is connected to the microscope column here near the source on the top, and the electrons are accelerated through 200 kilovolts in this particular column here. If you come a little closer, what you see here is the oil diffusion pump at this portion, and right here it is connected to, in this particular instrument manufacturer, you call it as a sputter ion pump. This has a 200 liter sputter ion pump, or the other manufacturer calls it as the ion getter pump. The vacuum system of the microscope, as informed, it runs under ultra high vacuum, and to obtain basic vacuum all through, you have a few roughing pumps in the background here. So the roughing pump is connected to the oil diffusion pump. In some cases, you may have a turbomolecular pump, and once you achieve about 10 to the minus 3 or 10 to the minus 4 millibar, your oil diffusion pump starts on, and once you steadily achieve a vacuum of around 10 to minus 5 millibar, that is when your sputter ion pump takes over, and that is how you achieve ultra high vacuum in a microscope column. We'll move gradually to the other side where the electric console is. So here's your electric console, and typically once you come to the microscope, a good practice is to check if this LED is on, if you are using a joule instrument. So you can just look out what the current reading here is for the sputter ion pump. This gives an indication that your ultra high vacuum, especially the vacuum reading on the sputter ion pump, is at a good value. And once you check that all this is ready, you can start by loading a sample and inserting the holder into the microscope. Now, if this is not ready, what you need to check is there are various reasons what could be wrong. One could be a simple shutdown of the lens. It could be a lack of supply of chilled water, or it could be any other reason. It could be a previous user not removing the holder properly. So we'll look at the software interface and then see what could be the reasons why an instrument might be off. But if these lights are on and all the readings on your screen are okay, you are in principle ready to go and insert a holder into the microscope. We'll quickly have a look at a few more details here. So this is your roughing pump. There's a little lead block in which the vibrations are damped, and the power console and the tubes here are to supply or circulate chilled water into the microscope column. So if you look at a chiller, this is how a typical chiller connected to an electron microscope, a TEM, looks like. You can see the readings here. It just gives you the temperature of the water that is being circulated in the microscope column. Remember, when you're using electromagnetic lenses, they often get heated up, and to maintain the lens uniform at a given temperature, you're circulating chilled water. If you come in closer, so here's the chilled water that is being pumped in. It is typically deionized water, and as long as this is circulating, you do not have an issue with the chiller. Sometimes it so happens that you have an error on the chiller, and this could be one of the reasons why your microscope stops. Yeah. So as you've seen, the general layout of any transmission electron microscope is you withdraw the power from the main line, which is either 230 volts or 110 volts, depending on where you are. And from there, if required, this instrument being from a Japanese manufacturer, we have a step-down transformer. And with the power situation in India, we generally have an uninterrupted power supply. So the raw power goes through our UPS and then to the step-down transformer. And from the step-down transformer, we power on the electric console. And once you check that everything is in order with regard to the power and the vacuum and so on, you are good to go and start loading a holder into the microscope. So here we have the JOL JEM F200 microscope. It's a cold field emission gun TEM operated at 200 kV. This instrument is also equipped with an EDS detector. If you remember, in the previous lectures, you've seen an example of the 2100 TEM, which has a lanthanum hexaboride filament. If you remember your lessons on the types of emitters, you have thermionic emitters, you have Schottky FEGs, and then you have a cold field emitter. So the idea is, this cold field emitter has a tungsten filament which is maintained at room temperature, and every day you want to use the instrument, you do a quick flash. So when you flash, what you do is you remove any oxide or a redeposited layer on the tip of the filament, and this is an automated process now. Earlier this was all manual control and through turning of many knobs, and it was more difficult to maintain a cold field emitter. But thanks to the automation now, you can actually do a flashing every day. Although the stability of a cold field emitter is much lesser than a thermionic emitter, or in comparison with a Schottky emitter, the stability is not as good. You can actually do multiple rounds of flashing through the day and then still keep the instrument running. The advantage is the FEG, the gun assembly, the FEG itself has a significantly longer lifetime than a Schottky FEG. So here is where your field emitter is, and this section consists of your condenser lens, the objective lens, and the apertures. In this instrument, all the apertures and everything is concealed. You do not see them. Here is where your specimen holder goes into the microscope. You have the illumination lenses again here, the binoculars and the fluorescent screen over here. Now, this instrument also has a fluorescent screen camera. So you have a camera which is pointing towards the fluorescent screen here, and you can record and see the live images on the fluorescent screen on the microscope computer. If I go down, going back to the layout that we saw, whatever is concealed here also contains a CMOS camera in this particular microscope. And if you move here, the layout is pretty much similar. So this is how the high tension tank looks like. And you have some water flow controllers here. Here's where the chilled water comes from the chiller, similar to a system that you saw in the previous videos. And then all of them are here to control the flow rates to different lenses. So you have water-cooled lenses in this instrument as well. And if I go to the other side, you have the electric console. So similar to the way you saw on a 2100 microscope, you can read the sputter ion pump readings here. Okay. So even this microscope has a roughing pump, which is typically a membrane pump or a scroll pump. And then this is kind of a backup pump to the oil diffusion pump. Even this microscope runs on an oil diffusion pump. Alternatively, you would have FEG instruments which also run on turbomolecular pumps as well. And once the oil diffusion pump achieves a vacuum of something in the range of 10 to the minus 5 Pascal, you have 3 sputter ion pumps, or the other manufacturer, Thermo Fisher, calls them the ion getter pumps. So you have a 200-liter sputter ion pump which is connected to the gun chamber here. And in between the gun and the column, you have another 150-liter sputter ion pump. And on the column where the specimen area is, you have another 300-liter sputter ion pump. So the idea is, in a cold field emission microscope, which is extremely sensitive to ultra-high vacuum, to have more stable emission, you would want to maintain as good vacuum for as long as possible. And this is achieved with a combination of several sputter ion pumps as well. So in this system, you have 3 of them. And the operation sequence is also similar to the other microscope that I told you.